All right. We are going to keep going in cycles, and we have ourselves the pendulum. Hi, Bob. Remember, if I do one of these, Bob's just going in circles, right? So, we can talk about conservation of rotational kinetic energy, same as we would talk about conservation of energy. So, let's pretend the pendulum, Bob, there starts down at the bottom. We move him to a location where he's horizontal and just let it go. Someone should write a song. So then Bob starts swinging back and forth. The radius of that circle is the same as the height at which Bob was elevated, right? So we will ask ourselves, what's the rotational velocity at the bottom? It's the same thing we did when we talked about kinetic energy, the 1/2 mv squared. I'll show you how it works out to be the same. But we'll say the sum of the energy at the top, which is up there, is the same as the sum of the energy at the bottom, which is right there. Now, sum of the energy mgh. Okay, now we said that h is the same thing as the r, so that's where that goes. It's equal to the rotational expression for kinetic energy, which is 1/2 I omega squared. Now, the I of Bob is simply mr squared. Okay, that's the I for a just a pendulum or a hollow ring hoop cylinder thing along those lines. So what I'm going to do, I will rewrite it. I will say this is mgr is the same thing as 1/2 is that 1/2 mr squared, and don't forget that omega squared. All right, so that is what we're eyeballing there. And remember what we said last video, that you already know, V is equal to R omega. So if I have an R squared times an omega squared, well, shnikes, that's the same thing as a V squared. So what I have written in green is just a side note. You see how this is the same expression for linear. We just never shared it with you because we haven't gone in circles yet. But I can say 1/2 mr squared omega squared is the same thing as 1/2 mv squared. So it's the same expression for linear. All right, but we're going to keep it going in circles because we're in the circles topic. So I'm going to have mgr equals 1/2 mr squared omega squared. I'm going to kill what needs killing. What that means is what that r dies with the square of that r, and we can kill the masses. So what I end up with is nothing more than little g is 1/2 r omega squared. Rearrange it. 2g over r square rooted is the rotational velocity that that sucker has when it is at the bottom of its trajectory. Okay, now the other example I will use, exact same situation, only it will be something like this. This again we've used before. This is just a ruler, but if we call it a rod and I just let go of the rod like that and have this sucker go back and forth. So this is a rod like all right. So the speed at the bottom here, if I hold rod horizontal and just let it go. Okay. So again, rod has a certain length. It doesn't matter. Just remember, gravity only cares about rod's center mass. So what we're concerned with in that change in height is the change in height of the center mass of rod. And so that's half of his length for that center mass. So we will get the omega at the bottom. We will use the exact same strategy RE, where we'll say the sum of the energy top is equal to sum of the energy to bottom. Now, MGH, that H again is L over 2. And again, if you don't know it yet, you need to get more familiar with these. The I of a rod that is pivoting about its end is 1/3 ML squared. All right, so what I will do is just rewrite it. This is MG, and I'll write it as 1/2 L. That'll help you visualize what we will end up killing. So this 1/2 is that 1/2. Then I'll multiply that by 1/3 ml squared and multiply that by omega squared. All right, so That's why I didn't go ahead and multiply the 1/2 by the 1/3, because you can tell when we go to cal what needs calling, we can kill the 1/2. So I'll just eliminate those, and we can once again kill the masses, and that L kills the square of that L. So after all that cal in, I have what? A GL is equal to 1/3. Whoops, no, I didn't kill that L. Jeepers. Come on, V. Ah, I would owe you push-ups, wouldn't I? Eh, eh, heh. Hmm. I have nothing more than little g is equal to 1/3 times that L times omega squared. So then when I rearrange it, the omega is simply the square root of 3g over L. Okay, so that is how fast it would be going in cycles at the bottom of its trajectory. Okay, so those two examples, just know how to use conservation of energy for different expressions, doing math with letters. Now, work. Remember, work, linear, force times distance. Okay, sometimes a distance is called a delta x, an xf minus an xi. Now, we also called it a dot product, okay, when you take two vectors and multiply them. And if their maximum value is when they're parallel to each other, then you use the cosine function. So a f dot d, or sometimes it's called an r, because the resultant vector is however far you have gone in whatever direction you end up going. But that force times distance times the cosine and the angle between them is what work is. Now for circles, again, forces are replaced with torques, so F's are replaced with taus, and distances, or x's, are replaced with thetas. So we have a torque is equal to a delta theta. So a torque times a change in an angle, which is a change in location or position along a circle, is the change in energy, and the torque delta theta is 1/2 I times the change in rotational velocity, okay? Because the 1/2 and the I are going to be constant unless we get to momentum, which we will do in our next set of notes. We'll say hi to Tony. Little Romo, huh? But let's do this example, an exercise bicycle wheel, all right? So it's going to be a stationary bike. It's initially not moving, so its initial velocity is 0. Then you get on that sucker, you start applying a torque. 18 Newton meters, you're fighting 2 Newton meters worth of friction. You go through that sucker 50 revolutions. Its radius is 18 centimeters. I went ahead and just told you the I, numerical I, is 2.5. So we're going to get the final velocity, rotational speed, and then what's the linear velocity way out on the rim there. Please remember, if you're going to do rotational calculations with thetas, we're going to go from revs into radians. So I'm going to multiply that by 2 pi, and that is equal to 314, I believe. 314 radians. And another one to remember, we're not going to call it 18 centimeters. We will call it 0.18 meters. All right, so make sure all that is in order. So work is equal to that change in energy. Okay, so the sum of the torques is times the change in the angle is equal to the change in the energy. All right, which is the change, the final minus initial. Okay, you guys all know if it started out with none, then it'll have none at the beginning. So the sum of the torque was what? 18 Newton meters, and I will subtract 2 Newton meters worth of friction. So that's the net torque. I'm going to multiply that by 314 radians. So there's the torque times the change in the angle. 1/2. Now remember, the I was given. It's not one you'll have to write an expression for. It's times 2.5 kilogram meters squared, and then we will multiply that by the omega f squared. So all I'm going to do is just push the divide button, which I guess I should have just done it with letters first, shouldn't I? Jeepers V. So when you divide that anyway, I will end up with what? 16 times 314 divided by half of 2.5. So put that in parentheses, put that in parentheses. Anywho, this ends up being 63.4 radians per second. All right, so that's the speed at which that bicycle wheel is rotating. That is an omega. All right, that's a rotational velocity. And if you remember, linear velocities are nothing more than those rotational velocities multiplied by however far you are from the centaur. So it is 0.18 meters multiplied by that 63.4 radians per second. So the radians, again, is nothing. That's how you end up in a meter per second. This is that quantity ends up being, I don't know, 11 and a half-ish, 11.4-ish. This is meters per second. All right. So please getting, well, just realize you can do the same thing going in circles as you did going straight. And holy shnikes, another example of that power. The rate at which work is done, all right? The rate at which energy is changing how it's expressing itself. Work divided by time, we can also call it a force times distance divided by a time, and you know that distance divided by a time is how you spell the letter V, all right? Since work was a force times distance times a cosine of an angle, power is a force times a velocity times the cosine of an angle. It is another dot product, okay? Maximus when parallellus, all right? So I just rewrote it that way too. And again, power is a scalar. It is not a vector. I forgot to mention that with work. Whenever you have dot products, your answer is a scalar. It's two vectors multiplied together to give you something without direction. What's that like? Remember algebra? Power, again, is a change in work or a change in energy. It's the amount of work that is done in a given time interval. Calculus, all I'm going to do is change the triangle and it becomes a differential, a dw over dt. So this then changes in work over larger time intervals. That would be an average amount of power that's extended over an interval of time. If I take a derivative, I will have an instantaneous rate at which energy is changing the way it's expressing itself, an instantaneous amount of power. And I can rearrange this, and this is a power times the integral of the derivative of time. So power times time is work if you write it integrally. For cycles, remember, you can do the exact same thing. Everything you did with a straight line, you can do going in circles. Remember that change in work, which is a force times a distance, right? Which is what I wrote here, a force times distance divided by a time. You can replace forces with torques, distances with changes in angles, positions along a circle in an interval of time. So again, that torque times change in theta divided by a delta t, a time interval. That again is an average amount of power that is being exhumed as over a interval of time. If I take a derivative of that, it will be a more instantaneous rate at which energy is expressing itself or changing how it's expressing itself. So a differential work with respect to time ought to look identical to that formula right there because it's identical to that formula right there. So again, everything that happens in straight lines can happen in cycles. A differential work related to time, you can rearrange it to look exactly like that. And hey, with that, we've gone in a few circles here. The calculus version again is the same as the algebra, just change a triangle to a D. And just remember the difference between a differential equation and integral form. But you guys should be pretty darn good at that by now. And remember, oftentimes they're going to do equations or going to do math with letters, not numbers. So when they'll say write an expression for it, it just means, kill what needs killing, do all the math with letters and end up with whatever it is that you end up with down at the bottom there. All right. So we will continue our journey with math with letters. And again, I'm just scrolling through all those I just put numbers in to give you something to work with here. But anywho, that's power, the rate at which work is done. You can do power linearly or circularly, and torques times delta thetas. All right. So Anyway, coming up on 15. Yay.